So today we talked about slope and rate of change. And one of the things that we found over the last handful of years in math is that we haven't done a great job of relating slope to the concept of rate of change. You guys learned slope as freshmen or eighth graders in algebra, and it reappears later on in your upper class math classes as rate of change, and sometimes the connection isn't quite there. So it's really important that we emphasize that fact, that is what slope actually is. So we start to think about a definition for slope. Okay? And its most basic, slope is a ratio, okay? A comparison of two numbers by division, and what we're comparing is a vertical change to a horizontal change. So slope is a ratio of vertical change to horizontal change. And we can also say that slope describes the steepness of a line. So a couple different ways that we can think about this. You probably remember from Algebra 1 that we use the letter M to represent slope. You also remember from middle school that commonly you guys talked about slope as rise over run. We want to think of it in a couple different ways though. Not only are we talking rise over run, rise being a vertical change, run being a horizontal change, we're going to think about it as the change in the y value. And that triangle is a capital Greek letter delta. We use it to represent change. So delta y over delta x. Change in y over change in x. And now that we're thinking about independent and dependent variables, we're talking about the change in the dependent variable over the change in the independent variable. So as we start to think about slope as a rate of change, now we're talking about the change in one quantity as it relates to a change in another quantity. And this is particularly important when we start to think about slope as it appears in word problems. All right, moving on. So you remember the formula for finding the slope of a line if you're given 2 points. We say m is equal to y2 minus y1 divided by x2 minus x1. So we're taking 2 points, taking the y coordinates and subtracting them, taking the x coordinates and subtracting them, and writing those as a ratio. So let's take a look at one example of that. In fact, what I'd like you to do is go ahead and pause the video even and work through this problem on your own, and then we'll check it together. So we write the formula as m equals y2 minus y1 over x2 minus x1. Two super important things. Let's actually go right to those ordered pairs and let's label them x1, y1. The second one, label x2, y2. You can go in any order you want. You can make these opposite. This could be x2 if you want it to be. And this could be the x1. As long as you remember that if you subtract in this order for your y's, you have to subtract in that order for your x's as well. So let's take a look at what that looks like. So let's go y2, which was 2, subtract off the y1, which was 5. Similarly, we start with the x2, which was 3, and the x1, which is negative 1. And then simplify. So 2 minus 5 is going to give us negative 3. Subtracting a negative, same as the adding a positive, right? So 3 minus negative 1 is the same as 3 plus positive 1, which is 4. And so you end up with a slope of negative 3/4. One of the beautiful things about the slope number is, without even looking at the graph, you can tell a little bit about what the line is going to look like just from its slope number. So a slope that's positive is going to result in a line that increases from left to right. We say it rises. A slope number that's negative is going to result in a line that decreases from left to right. We say it falls. If the slope number is 0, you're going to end up with a horizontal line. And a slope number that's undefined results in a line that's vertical. And it sounds like a strange thing. How can you end up with a slope number that's undefined? Well, if you remember right, in the set of real numbers, dividing by 0 is not defined. How can we end up with 0 in the denominator of a fraction, a slope fraction? Only way that can happen is if your x values are the same. Vertical line, every single point on that line is going to have the exact same x value. When you subtract them, you're going to end up with 0. Results in an undefined slope. Let's take a look at a couple more examples. So without graphing, tell whether this line through the given points rises, falls, is horizontal, or is vertical. So the 2 points, negative 4, 1, negative 1, negative 2. And using our slope formula, y2 minus y1 over x2 minus x1. Negative 2 minus 1 over negative 1 minus negative 4. Negative 2 minus negative 1 gives us negative 3. Negative 1 plus 4 is positive 3. Negative 3 over 3 is going to give us a negative 1. We know that a negative slope is going to decrease from left to right, so we say it falls. And that's the way the work would look if you saw this on a quiz or a test. Next example, we want to be able to tell which of two lines is steeper without actually seeing the lines themselves. If we're just given 2 points on each line, how can we do that? Well, the idea of steepness, if you've been around town, if you're walking up Campbell from, say, Ogden to Northview, kind of a gentle uphill slope, but you feel it if you're walking, running, or riding your bike. And it's great when you're going down that hill, too. Feel like you're flying. Compare that to riding or walking your bike farther up Campbell by Rogers Lakewood. Steeper hills. Much harder to work. So what would make a line steeper? It turns out that we're talking about which one has the greater absolute value. Not worried about the sign, worried about the absolute value of the number. So the slope of line 1, y2 is 5, y1 is 0. x2 is 1, x1 is negative 3. 5 minus 0, 1 plus 3. So a slope of 5/4. The second line, 1 minus negative 6, 4 minus negative 2. So between 5/4 and 7/6, which of those is going to have a steeper slope? The 5/4. Lastly, we talked about slope as a rate of change, and especially applying when we look at word problems. So let's take a look at this one. Camping at the north rim of the Grand Canyon at an elevation of 8,200 feet. So when it's 75 degrees at your camp, it's 104 degrees at the floor of the canyon along the Colorado River. What's the average rate of change of temperature as elevation decreases? Well, we need to start thinking about putting together some ordered pairs. What information do we have? We know elevation and temperature. We know elevation and temperature. We need to decide one of these to be our independent variable and the other to be our dependent variable. Well, temperature is going to depend on elevation. So our elevation is going to be our x value. So let's start with our first elevation, 8,200 feet. And our temperature, 75 degrees. x1, y1. Our second elevation, x2, 2,400 feet. And temperature 104 degrees. x2, y2. So let's go ahead and set up a slope formula. y2 minus y1, 104 minus 75. x2 minus x1, 2,400 minus 8,200. Bigger numbers, so go to your calculator. 104 minus 75. Difference of 29 degrees. Difference in elevation, 2,400 minus 8,200, negative 5,800. Both of those values divide by 29. So we get a rate of change of negative 1 over 200. Well, that's great. What does that mean? Well, they asked the question in words. We're going to answer the question in words. We're asked the average rate of change in temperature with decreasing elevation. So our temperature is going to increase 1 degree Fahrenheit for every 200 feet of elevation change. All right, and that is calculating slope, applying slope to determine which of two lines is steeper, and applying slope as rate of change in a word problem.